So this is an assignment which is related to gravitational fields. And we'll do the first question. The first question, Select 1, was the first Earth orbiting space station. It was built by a Soviet Union and launched into a low Earth orbit 50 years ago. The orbit at an average height above the Earth was 211 kilometers. The mass is given for the Earth and the radius is also given. The textbook claimed that the astronaut in this space station, there would be sunrise 16 time every day. Like basically, it will move around the Earth 16 time in one day. That we have to show. Assess the validity of this claim. We have to check whether this claim is accurate or no. So how we can work out? First thing, what we will do, we can like using the idea as it is moving. So we will find the orbital time, like how much time it is taking, and then using that we can, because we'll divide by in 24, like we'll first mainly find the orbital time. So how we can work out the orbital time? So this is the Earth, and this was a space station, the first orbiting space station. So this was the orbiting space station, and its height above the Earth is 210. So this distance was 210 kilometer or 211 kilometer, and the radius of the Earth is 6.3 exponent 6. This total distance is 6.3 into 10 to the power 6 meter, not kilometer, meter. 6.37 exponent 6 meters. So we should have both in the same unit, like it should be like 211 into 10 to the power 3 meter. Now what we will do, we have the radius, and what we can do, we can work out the circumference. How we can work out the circumference? Circumference will be equal to 2 pi r. So after knowing the radius, multiply by 2 pi, we'll get the circumference. After knowing the circumference, we'll find the time period. For one complete revolution, how much time it takes. So we have the formula, speed is equals to distance over time. As the speed is not given, after knowing the circumference, we can also work out its speed. As we know, speed is equals to distance divided by time. So distance will be equal to 2 pi r and time is t. So, and when this object is moving in a circular path, the force of the, like the centripetal force is there. That centripetal force is equals to m v square over r. That is the centripetal force which the object experiences. And because this centripetal force is equals to gravitational force, so when two objects, they have a gravitational force, so the formula is g m1 m2 over r square. So the mass of the Earth, the mass of the satellite divided by r square. So when we compare the two equations, because the gravitational force is equals to centripetal force, so we compare the two equations. G is equals to m1 m2 over r square is equals to mv square over r, and this one will be m1. So this m1 will cancel with m1. M1 is the mass of satellite and m2 is the mass of the Earth. So if I write me here, m1 will cancel with m1, r square and r will cancel. So it will be g divided by multiplied by me divided by r is equals to v square, and we take a root. So this will give us g, the mass of Earth, divided by radius. This is the radius, distance from the center, in a root, so we'll get the speed. So this will give us the speed, and now we will use this formula. Speed is distance divided by time. So if we need a time, time will be distance divided by speed. So time is equal to distance. Distance will be circumference to pi r, and speed what we get here. So we have the speed. We have radius 2 pi, so we work out the time period of this space station, orbiting space station. And after getting a time period of this orbiting space station, we just divided like 24 divided by time period, so we'll know how many times it will move around the Earth. And that will be approximately 24. Is it clear, this part? So using the gravitational potential energy, using the gravitational law of gravitation and the centripetal force, we work out the speed, and speed is distance divided by time, so we'll work out its time period. Then the Salyut 1 made most 3000 orbits before falling back to Earth. Calculate the change in the gravitational potential energy as it fall back to the Earth. So as it fall back to the Earth, it's not the, basically what we will do, like this is our Earth. So as it fall back to the Earth, it's not, its radius won't be zero because there is a radius of Earth. So this was a total distance from the center, which is equals to radius of the orbit above the Earth atmosphere, which was 210 km, 211 into 10 power 3 meter, and this was 6.3 into 10 power. The radius of the Earth was 6.37 exponent 6. So this was 6.3 exponent 6. So how we can work out its change in the gravitational potential energy? So potential energy for the satellites or the gravitational potential, you can also work out. It is given by, like we first will work, because the value of the gravity is changing, so we cannot use that formula mgh. That won't give us the right answer because the gravity is not constant there. So the formula which we use for satellite gravitational potential energy, or the change in gravitational potential energy of satellite, or the gravitational potential is given by a formula G M over R. That's a formula. So what we will do, G is the gravitational universal constant, M is a mass, what we'll use, the mass of the Earth we'll use here, and R, what is R1 and R, like what is R here? First we'll find the gravitational potential energy at this point. So for a satellite, this is giving us a gravitational potential, and to get the energy, the gravitational potential energy for the orbiting objects, that is M into delta V. And what is delta V? Like this is a gravitational potential which is Gm over R. So first we'll take R1 and then we'll find the gravitational potential using the same formula Gm over R2. So first we'll find the gravitational potential at this point, then we'll find the gravitational potential at this point, and we take a difference, then we'll get the change in gravitational potential. And to get the gravitational potential energy, it will be multiplied by mass. So when we multiply by mass, we'll get the gravitational potential energy. The only difference, the distance which we use R1 and R2. When we use R1 example, that will be the sum of 6.37 into 10 to the power 6 plus 2.11 into 10 to the power 3. Or 200, not 2.11, it's 211. And when we take the R2, and R2 will be equal to 6.37 into 10 to the power 6. That's it. And we substitute here, we get the gravitational potential energy, gravitational potential, not energy, the gravitational potential at the height 1 and then height 2, like at the on the Earth surface, and just take a difference of the gravitational potential to know how much the change in gravitational potential. And change in gravitational potential and multiplied by mass will get the change in gravitational potential energy. Or you can also use this formula that for satellite, the potential energy, like normally when we use the potential energy, we say mgh, okay? But because the value of the G is not constant, so how we get this G? It is given by a formula. G is equals to, the value of the G is equals to M over R square So when we simplify this, it will be m. This is G, capital G. The value of the G is equals to capital G m over r square. So in place of G, if I write G m over r square and the height is r, h. So we cancel out. So it will, we are left with this is a mass of object, this is a mass of the planet. So it will be m g m over r. That is actually how we work out the potential energy for satellites or objects which are orbiting the Earth. So mass of object, mass of the Earth, gravitational constant, and r is a distance. So we'll work out the potential at the orbiting radius. Then we'll find the potential on the surface of Earth and just take a difference to know how much the gravitational potential energy changes. Then the last part, it burned up over a Pacific Ocean and it re-entered the Earth. So just why it burned up? What is the reason for that? Because when the satellites or the object, stellar object, enter the Earth atmosphere, what happened? The Earth, there's a friction, there's a drag, and that drag force produce heat energy. So there's the objects will do a work done against the drag, and that causes an increase in temperature. As a result, as the energy, like that work done transfer as a heat energy, and that increases the temperature of the satellite. So there's a drag or a force acting on the satellite. So there is a work done which produce the heat energy. As a result, the temperature will increase.